Good morning, everybody. I welcome you all to this series of lectures on electronic device and circuit subject. I am V.R. Seshagiri Rao, Associate Professor in the Department of Electronics and Communication Engineering, IARE. Today, I am going to discuss on the clamping circuit theorem. Before I discuss the clamping circuit theorem, I will just summarize the clampers. So, what is a clamper? Clamper is a circuit that adds a DC level to an AC signal. So, actually, the positive and negative peaks of the signals, you can shift them as per the design of the clamping circuit. So, as the DC level gets shifted, the clamper circuit is also called as level shifter. And clamper circuit, naturally, it consists of energy storage elements like capacitor. So, in the clamping circuits, what I am going to discuss today, they contain essentially a capacitor, a diode, a resistor, and a battery to provide a reference voltage. And let me quickly summarize the clamping circuits. We have positive clamper, then positive clamper with positive VR, positive clamper with negative VR, negative clamper with positive VR, and negative clamper with negative VR. So these are the various types of clampers. Now this circuit, it is a positive clamper circuit. So you can see this is a waveform, input waveform with average value as 0. So and it is shifted up. So it is a positive clamper. Now you see the whole waveform starts from 0. So it is shifted upwards, positive side. So it is a positive clamper circuit. So how it works? So initially the charge across the capacitor is 0, and when the voltage is negative, then the diode is in forward bias and the capacitor gets charged to Vm, and thereafter the output voltage V0 is equal to Vi plus Vm. Vm is the voltage across the capacitor when it is fully charged, and this takes place when the diode is in forward bias during initial negative half cycle. So thereafterwards, when the voltage is Vi, the voltage Vi is at peak Vm, then what is the output voltage? Vm plus Vm, so it becomes 2Vm. So the positive peak is going to be 2Vm of the output voltage. And when the voltage is its negative place, negative peak, then Vi is minus Vm and V0 is equal to minus Vm plus Vm, so it is 0. So at the negative peak voltage is 0, positive voltage peak is Vm. So this is how the voltage is clamped to the positive level. So the input waveform is clamped in positive direction. Now the same circuit, when we give a reference voltage VR, then what happens? The voltage is shifted further up by the reference voltage VR. So how it happens? Initially when the voltage is negative, so during negative portion of the waveform, this diode is in reverse, this diode is in forward bias and the capacitor gets charged to Vm plus Vr. So capacitor gets charged to Vm plus Vr. Vr is the reference voltage. And what is output voltage? Output voltage V0 is equal to Vi plus Vm plus Vr. So when during the initial negative portion of the waveform, the diode D is in forward bias and the capacitor gets charged to Vm plus Vr. Vr is a reference voltage. Now in the steady state condition, when the voltage is a positive, then what happens? You get accordingly the proportional output. So during subsequent positive cycle, when the voltage is at plus Vm, then the output voltage V0 is equal to Vm plus Vm plus Vr. So it is going to become 2Vm plus Vr. So this peak voltage is going to be 2Vm plus Vr. And and when the voltage is negative, when the applied voltage is negative, the minimum voltage is Vr. So this is the minimum voltage during the negative peak of the input waveform. So this is Vr. So depending upon the reference voltage, further shifting of the input waveform can be done during using this positive clamper circuit. Now let us discuss about the negative clamper circuit. So this is the negative clamper circuit. In negative clamping circuit, the input waveform is shifted down. So you see here, the average value of this input waveform is 0. Now you see here, it is shifted down below 0 volts. So that's why this is called as negative clamper circuit. So how it happens? Here, the output V0 is equal to Vi minus Vm. That is the output voltage. Okay. So when the voltage is positive, so during the first positive half cycle, the diode B is in forward bias and the capacitor gets charged to Vm. So during the first positive half cycle, the capacitor gets charged to Vm. Okay, and in the steady state condition, when the input voltage is at its positive peak, then what will the output voltage? When the input voltage is at positive peak, then V out is equal to Vm minus Vm, so that is equal to 0. So during this positive peak, the output voltage is 0 during steady state condition. Now when the voltage is negative, then when the voltage reaches the negative peak, then the output voltage V0 is equal to, so at this point Vi is equal to minus Vm. So you get V0 is equal to minus Vm minus Vm. So you get minus 2 Vm. So you can see here this is minus 2 Vm. So this is how the negative clamper circuit works. Now for all our discussion of the clamper circuit, we assume that the charging time constant is very less compared to the discharge time constant. So that means RFC is far less than RC. What is RFC? RFC is the charging time constant, and we assume that the charging time constant is far less than the discharge time constant. Typically the values are chosen in such a way that RC is equal to 10 RFC. RC is equal to 10 RFC. So this is how the negative clamper circuit works. Now let us discuss about the negative clamper circuit with negative reference voltage. So this is the circuit with negative reference voltage. So the difference between earlier circuit and this circuit is we have added a negative reference voltage, which further causes the shifting of the input signal by VR. An additional shift of VR is introduced in the output waveform. So a negative clamper circuit, if biased with some negative reference voltage, then voltage will be added to the output to raise the clamped level. So using this, the circuit of the negative clamper with negative reference voltage we can construct as shown here. So here what happens, the cathode of the diode is connected with the negative reference voltage and which is less than that of 0 and the anode voltage. So when the circuit works like this, when during the positive half cycle the diode is forward biased and the capacitor gets charged to Vm plus Vr. So the capacitor gets charged to Vm plus Vr. And what is the output voltage? So the output voltage V0 is equal to Vi plus Vm. Sorry, this is a negative reference voltage, so it's a Vm Vi minus Vm minus Vr. So when the voltage is positive, then the output voltage is Vm. So output voltage V0 is equal to minus Vr. So during the positive peak, you get the output voltage as minus Vr. So during the positive peak, Vi is equal to Vm. So the output voltage V0 is equal to minus Vr, because during the positive peak V0 is equal to Vm plus Vm minus Vm minus Vr, because during the positive peak Vi is equal to Vm. So the output voltage is equal to Vm minus Vr, so it becomes minus Vr. So you get like this. This is a minus Vr. And during the negative peak, what is the output voltage? V0 is equal to, during the negative peak, Vi is equal to minus Vm. So you say minus Vm minus Vm minus Vr. So you get output voltage as minus 2Vm minus Vr. So this voltage is going to be minus 2Vm minus Vr. So to the negative clamper circuit, if you put a negative reference voltage, the waveform gets an additional shift of Vr downwards. So what are the applications of the clamper circuits? The clamper circuits are used as direct current restorers. They are also used to remove the distortions. They are used as voltage multipliers. They are used for protection of amplifiers. They are used as test equipment. They are also used as baseline stabilizers. So the applications of clampers are: they are used as direct current restorers. They are used to remove distortions. They are used as voltage multipliers. They are used for the protection of amplifiers. They are also used in the test equipments, and they are used as baseline stabilizers. So these are the various applications of clampers. Now let us discuss about the clamping circuit theorem. So the clamping circuit theorem, it states that under steady state conditions for any input waveform, the ratio of the area under the output voltage curve in the forward direction to that in the reverse direction, it is equal to the ratio Rf by R. So this is a clamping circuit theorem. So the clamping circuit theorem, it states that under steady state conditions for any input waveform, the ratio of the area under the output voltage curve in the forward direction to that in the reverse direction is equal to the ratio Rf by R. RF is the diode forward resistance and R is the diode reverse resistance. So this is the circuit. So when the diode is on, see it has a resistance of RF and this is the area AF. And when the diode is in reverse bias, this is the area. And these areas, they follow the ratio of RF by R. So AF by AR is equal to RF by R. So that is a clamping theorem. Now to see this, let us consider a negative clamper and let us analyze the behavior of this circuit with square wave input signal. And initially when the input signal is positive, so this is a square wave form. So let us analyze the behavior of the signal with a square wave input. So initially the voltage across the capacitor is 0. So when the input voltage is maximum, then what happens? The capacitor gets slowly charged towards the it gets charged, and when it gets charged, then what happens? The diode is in forward bias and the capacitor gets discharged. The capacitor gets discharged. So you see here the capacitor is charged to the peak value, okay, and as time goes on, when the capacitor gets slowly charged to the peak value, the voltage across the diode, it falls down. So it falls down in this way. And at this time, when the voltage becomes negative, then what happens? The diode is in reverse bias and all the input voltage, it appears across the load like this. Then what happens? Slowly the capacitor gets charged in the reverse direction and it follows this curve. It follows this curve. So here the clamping theorem, it states that AF by AR is equal to RF by R. RF by R. So there is a clamping theorem. Now let us see how it works. Now during the interval from T1 to T2, okay, when you apply a positive pulse, the diode D is in forward bias and the capacitor gets charged. And let IF denote the charging current. So this is charging current IF. So let us denote this current by IF. Okay. So initially when you give a signal like this, what happens? The diode D is in forward bias and there is going to be a current, and let that current be IF. Okay. And because of this current IF, the capacitor gets charged. So what is the charge that is accumulated on the capacitor? It is equal to integral of T1 to T2 IF multiplied by dt. What is IF? IF is the current when the diode is in on condition. So this is a current. So Q dash is the charge acquired with the capacitor. Charge acquired by the capacitor. Okay. So what is IF? IF is nothing but VF by RF. Because VF is a forward voltage across the diode. VF is a forward voltage across the diode, and RF is the diode forward resistance. So IF is equal to VF by RF. So Q dash becomes integral T1 to T2 Vf by Rf into dt. Q dash is equal to integral T1 to T2 Vf by Rf into dt. And Rf is a constant, so you can bring it out from the integral brackets. So Q dash is equal to 1 by Rf into integral T1 to T2 Vf dt. So Vf dt is the area, which is nothing but AF. So Q dash is equal to 1 by Rf integral T1 to T2 and Vf dt. So integral T1 to T2 Vf dt, it is nothing but AF. So we can say that Q dash is equal to AF by Rf. So Q dash is the charge that is acquired with a capacitor. Q dash is the charge acquired with a capacitor. Now, what is the charge lost? The charge lost by the capacitor when the diode is in reverse bias, it is given by this. So the charge lost is integral. So during this period, the charge is lost. So we can say that during T2 to T3, the charge is lost, and that is equal to, again you have to take the current, and current is given by VR divided by R. So R is this resistance. So VR by R into dt. So this is equal to 1 by R integral T2 to T3 VR dt. So what is this integral T2 to T3 VR dt? So this is the portion. So this, it represents the integral T2 to T3 VR dt. So this is nothing but AR. So this is equal to AR by R. So the charge lost is equal to the charge gain. That means Q is equal to Q dash. So what we have to do? We have to equate 1 by R T2 to T3 VR dt is equal to 1 by Rf T1 to T2 Vf dt. So AR by R is equal to 1 by Rf AR. AR by R is equal to 1 by Rf AF. So this gives us that AF by AR is equal to RF by R, which is nothing but the statement of the clamping circuit theorem. So let us quickly discuss the clamping circuit theorem, which is the main topic today. So the clamping circuit theorem, it states that under steady state conditions for any input waveform, the ratio of the area under the output voltage curve in the forward direction is to that the reverse direction is equal to Rf by R. Rf is the diode forward resistance. So here you can see that during the portion T1 to T2, the diode is on and the capacitor gets charged through the diode forward resistance, which is Rf. And during the portion T2 to T3, the capacitor gets discharged through the external resistance R. So this is that area. Now let us find out the ratio of these areas. So during the portion T1 to T2, the capacitor gets charged. So what is the charge acquired with the capacitor? The charge acquired with the capacitor is equal to T1 to T2 and IF dt. That is the charge acquired with the capacitor. So that is equal to IF is equal to Vf by Rf. So Q dash is equal to integral T1 to T2 Vf by Rf into dt. So Q dash is equal to 1 by Rf T1 to T2 Vf dt. So Q dash is nothing but the charge acquired with the capacitor. So integral T1 to T2 V of dt is equal to EF. And similarly, what is the charge lost by the capacitor Q? So the charge lost by the capacitor is in this direction, and in this direction we assume that the current to the diode is IR, and that is equal to 1 by R T2 to T3 VR dt, and charge lost is equal to charge gain. So we say that 1 by R integral T2 to T3 VR dt is equal to 1 by RF T1 to T2 VF dt. So that gives us AR by R is equal to 1 by RF AF, and putting it other way, AR by R is equal to AF by RF. So you bring AF here, or you can take AR this side, then you get AF by AR is equal to RF by R. So that's the clamping theorem. Now let us discuss about the comparators. So what is a comparator? A comparator is a circuit that tells at what time instant the input amplitude has reached a reference level. That is an amplitude comparator. So amplitude comparator, V0 is equal to 0 for t less than t1, and V0 is equal to V for t greater than or equal to t1. So what is the distinction between comparator circuits and the clipping circuits? In a comparator circuit, there is no interest in reproducing any part of the input signal waveform, whereas in a clipping circuit, part of the signal waveform is needed and that needs to be produced without any distortion. So there is a difference between comparator and clipping circuits. Now this is a comparator circuit built using the diode. So here we have given input signal in a ramped format. So the input signal is a ramped signal. What is a ramped signal? It continuously increases with time. So there is a ramp signal, and such a signal is given to this circuit. And the circuit has been provided with a reference voltage of VR. So VR is the reference voltage. VR is the reference voltage. So in this case, you see here, initially when the voltage is less than VR, what happens? The diode is in forward bias. So when Vi is less than VR, then what happens? The cathode of the diode is at a lesser voltage compared to the anode of the diode. So naturally the diode is in forward bias, and we get the output voltage as VR. So up to this portion during 0 to T1, you get the output voltage as VR. And at T1, when the applied voltage becomes greater than VR, then what happens? The cathode of the diode is at a more potential compared with the anode of the diode. So the diode is in reverse bias, and when the diode is in reverse bias, it acts like an open switch, and we simply get the input voltage at the output terminal. So at T1, when Vi is greater than VR, the diode is in RB, in reverse bias, and it acts as an open circuit, and the output voltage V0 is equal to Vi. So you see here at T1, we simply get the input voltage at the output. So this is how the comparator circuit works. And comparators, they can be non-regenerative or regenerative, and clipping circuits are of course non-regenerative comparators, and Smith trigger and oscillators are regenerative comparators. So this is the this is the comparator circuit which we have made using the diode. So the comparator circuit contains simply a diode and a reference voltage, and we have assumed that the input signal is in ramp format, which is continuously increasing with respect to time, and as long as the input signal is less than the reference voltage, the diode is in forward bias. So when the diode is in forward bias, it is simply denoted by a short circuit, and we get the output voltage as VR. And when the input ramp signal becomes more than the reference voltage, the diode becomes reverse biased, and in reverse bias, the diode acts as an open circuit, and the output voltage V0 is equal to Vi. So we get the input voltage as it is from T1. So this is how the comparator circuit works. Now let us solve this problem. Design a clamp clipping circuit with two ideal components which can give the following waveform shown in the figure for a sinusoidal input, and assume the necessary data. So we have to design a clipping circuit which clips the input sinusoidal signal at two levels, plus 5 volts and plus 10 volts. So we have to design this clipping circuit which clips at 2 points. Now first is, when you have to clip the signal at plus 10 volts, then we have to design a positive clipper circuit with positive reference voltage. So first, in the first stage, let us design a positive clipper with positive reference voltage. So this is R, and this is a diode, and this is 10 volts. So how this circuit works? When you give a waveform like this, let us say the peak value is 20 volts, and this is 0, and this is minus 20 volts. So this circuit, what happens, when you give the voltage like this, till this point, what happens, the diode is in reverse bias and it acts like a open circuit. So we simply get, okay, I'll explain the circuit in a different way. This is 5 volts. So this is a circuit that gives this type of waveform. So this is 0 volts, and this is 5 volts, and this is 10 volts. So this circuit will give this type of waveform. Let us see how it gives. This is the input signal, And let us say this is 5 volts, and this is 10, and this is, let us say, 20 volts, and this is 0 volts. Let us say this point is B, and let us say this point is C, and let us say this point is D, and let us say this point is E, and let us say this point is F, and let us say this point is G, and let us say this point is H, like that. Okay. So during the points from A to B, then this is a A, and during the points A to B, okay, the voltage is less than 5 volts. So when the voltage is less than 5 volts, what happens? This diode D1 and this is diode D2. So during A to B, D1 is in reverse bias and D2 also is in reverse bias. Sorry, D2 is in forward bias, because A to B the voltage is less than 5 volts. So as far as D1 is concerned, it is in reverse bias, but D2 is in forward bias because the voltage of the cathode is less than 5 volts. So what we get? We simply get 5 volts here. So I am simply getting 5 volts here. And from the points B to C, when the voltage is less than 10 volts, still the diode D1 is in reverse bias and D2 also is in reverse bias, because B to C the voltage is more than 5 volts. So the D2 becomes reverse biased and the output voltage is equal to the input voltage. So B to C, I simply get this shape. So I am getting this waveform like this. And from C to E or C to D, what happens? The voltage is more than 10 volts. So what happens? When the voltage is more than 10 volts, then D1 is in forward bias and D2 is in reverse bias, and the output voltage V0 is clamped to 10 volts. So I get this type of waveform. And in the points D to E, so again D1 is in forward bias and D2 is in reverse bias. So the output voltage V0 is equal to Vi. So we get this type of waveform. And from F to G, in F to G, the voltage is less than 5 volts. So when the voltage is less than 5 volts, what happens? D1 is in reverse bias, but D2 is in forward bias, and the output voltage is clamped to plus 5 volts. So we get this waveform. So like that, we have designed a circuit which has given this type of output waveform with a sinusoidal voltage. So this is how we have solved this problem. So let me again tell. So the problem is design a clipping circuit with ideal components. What is the ideal component? Ideal component is that a diode acts as a short circuit when it is in forward bias with a zero cut-in voltage, and a diode is said to be ideal when it acts as an open circuit with zero current when a reverse bias is applied to that. So we have assumed that the diode and the resistors and all the components are ideal. So with that assumption, we have to design a circuit which gives this type of waveform for a sinusoidal input signal. So this signal is clipped at plus 5 volts and plus 10 volts. So this is the circuit D1 and D2, and we have given a reference voltage of 10 volts here and a reference voltage of 5 volts here. Okay, and this D1 circuit essentially it clips the positive portion of the signal, and D2 it clips the negative portion of the signal. And the points between A and B, D1 is in reverse bias and D2 is in forward bias, so it acts as a short circuit, and the output voltage V0 is equal to plus 5 volts this way. And in the points between B and C, the voltage is between 5 and 10 volts, and in that case both the diodes are in reverse bias, and we get a waveform like this, replica of the input signal. And between C and D, D1 is in forward bias and D2 is in reverse bias, so the output voltage is clamped to plus 10 volts. And again between D to E, both are between D and E, when the voltage, D and E, the output voltage is equal to input signal, and we get the waveform in this fashion. So in today's class, we have discussed about the comparators. We also have discussed about the theorem, and we also have discussed about a problem which has clipped a sinusoidal signal at two different points. So these are the references what I have followed for today's class, and these are the textbooks I have referred to make this PPT. So with this, I conclude today's session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.